take a look on page 62. I am recording. So we're going to start here at number 6. We're just going to do one word problem. It's going to take us like 15 minutes to do it, but I'm hoping it motivates why do we care about these crazy things called differential equations. So we'll start with number 6. Joey? Okay, so let's think about this sentence right here. It says Newton's law of cooling is this crazy thing. Suppose that let's just guess what the room temperature is right now. 45 is a poor guess. So okay, so so we'll say the room temperature is about 70. Okay, so Evan has a Snapple here. Let's say that the Snapple has been refrigerated. So let's make an estimate. He just took it out of the refrigerator. So maybe the current temperature of the Snapple is 35. That's why I touched your bottle before. I wanted to see if it was cold. It's not. This whole thing is just a lie. But suppose it's currently 35 degrees. If we let the Snapple just sit here and we come back on Monday, what do you think the temperature of the Snapple will be? 70. I mean, if the room stays at 70, then the Snapple is going to just become eventually. Yeah, probably won't ever technically get there, but we expect it's going to head to 70 degrees, right? Okay, let's suppose that we look at some information between now and Monday. We're going to let the Snapple sit here, but 1 hour from now, let's say the temperature of the Snapple is 45. It's heated up 10 degrees. I would like to know 2 hours from now, can you guess, is the temperature of the Snapple 2 hours from now going to be 55, less than 55, or more than 55? A couple of votes for less. What do we think? Evan thinks more. So let's think about this. At the moment, the Snapple is 35 degrees. How far is the Snapple's temperature from the room temperature? Okay, so the difference at the moment is also 35 degrees, right? To get from 35 to 70. Now suppose we wait until the Snapple gets up to this. Now what's the difference between the room temperature? Now it's 25. At which moment in time is the Snapple more inclined to change temperature? When it's 35 degrees away from the right temperature, or when it's 25 degrees away? It's when it's 35. It has a lot of interest in getting to 70 degrees faster in the beginning. If we look, if we wait until like Sunday and it's at 68, the temperature is very close to the 70, right? The Snapple's at 68. It's, it's like, all right, I got to get a little bit warmer, but, it's not that big a deal. I'll get there kind of slowly, right? It's not going to shoot to 70 really quickly. It's going to go quick in the beginning, but then it's going to kind of slow down as it gets close to 70. And that's what okay, so then the 55, maybe, Joey says maybe 52. Fine. So that's all that Newton's law of cooling says, is that it says that the rate of change in the temperature, so in the first hour it changed by 10 degrees, in the second hour we're saying it only changed by 7. The rate of change is proportional to, at some constant, times the difference between the temperature of the Snapple and the external temperature. And that's the difference that we calculated there. The bigger the difference between the temperature, the more inclined the Snapple is to heat up, right? And that's what that says. What do we think? Will the temperature of the room decrease because the Snapple is cold? Theoretically, just a sliver, but it's so insignificant, right? All the 70-degree air molecules here are gonna, like completely absorb any kind of cold molecules that are coming off of the Snapple. But it's a good question. Yes, I would love to know why that's true. Also, technically, I guess if I jump up, the Earth is going to come meet me a little bit, right? Right, I'm going to fall towards the Earth, but the Earth is also going to fall towards me a little bit. Same kind of thing with the Snapple. Well, I have a lot of power. Okay, Josh, can we go to the next page, number 7?
Temperature of the room has been maintained at a constant 68 degrees Fahrenheit to the nearest
Minute. Okay, so this is a typical, what's that? We're on the next page. 70? What page are we on? 63. Okay, so this is a typical CSI question, right? They've got a body that's been found, and we don't know when the murder occurs. The body is just there. So the chief of police will ask the CSI, who's got to be some attractive person, when did this murder occur? And within moments, they will spit out an answer, oh, between, like 8 p.m. and 10 p.m. last night. And so let's see if we can figure out how this attractive CSI does this calculation. So let's start with some of the givens here. So we're going to okay, you don't need to write any of this stuff down. This is really just the motivational, why do we think about differential equations? So we're going to let t equal the time in hours since 9 a.m. And then we're going to let capital T, it's unfortunate it's the same letter, be the temperature of the body in degrees Fahrenheit at time t. Okay? What happens to the body once this unfortunate person is killed? What happens to the temperature? It's going to decrease, right? Because the temperature of a healthy body is 98.6. Does it ever strike you as strange, that number? That we have that much precision and it's, yeah, it's certainly not it's not a constant. Mm-hmm. Mm-hmm. But don't you think we would have found a nice number and just called it, like if it was really 98.6, wouldn't we have just rounded and said 99? Yeah. Yeah, 98.6 is not the original number. This study was done in Celsius, the useful measurement of degrees. It is pretty close to 100, isn't it? Healthy body temperature. So 37 degrees was the nice round number that this person got. And then we convert that and we get the ugly number 98.6. Okay, so what happens to the temperature of the body once they die? They start to cool off because it's kind of, it's 68 degrees in the room and their body temperature is starting off at 98.6. And so what we're going to do is try to find the formula for the temperature as a function of time. I know that, so this is definitely not the formula, but one way I could make it start at 98.6 and decrease would be something like this. In English, what is this saying about the temperature of the body? Decreasing linearly. What's this 5? 5 degrees every hour. Okay, so that's fine. It would take care of like start healthy at 98.6 and then decrease, but that would shoot us right past 68, right? We would pay no attention to the 68. So it's something more subtle than this, but this is the idea. Starts at 98.6, decreasing to the 68. But the goal is to find the real formula, not this made up one. So let's first get some of our givens out of the way. T of 0 represents the temperature at time 0. When is time 0? Our time 0 is 9 a.m. That's how we defined it. I don't know when the murder moment was, so I just defined 0 to be 9 a.m. So how much is the temperature at time 0? 90.3. So this is a given. And then the other time that we know about is t equals 1, because it says 1 hour later. What is the temperature? 89. So 2 givens, right? All we did is translate the info in the paragraph into our symbols. What do you know about t of x?
Well, yeah, but we know that at time some x, how will we have to figure out it's going to be?
Yeah, so why don't we put that? T of something that we're going to try to find is supposed to be 98.6, right? That's what we're going to do to solve this problem. it's going to be a negative number because it happened certainly before 9 a.m., right? Good. Okay, let's get to Newton's law of cooling. It says that I'll just say it, but this is what Joey read to us. It says the rate at which the temperature is changing. What does rate mean to us in a calculus class? It does mean slope. It means derivative. So the rate of change, which one is the dependent? Which one is independent? So temperature is changing because time is passing, right? So this is saying that the rate of change of the temperature, so the rest of Newton's law of cooling said is proportional to, is equal to a constant times, okay, some constant, the difference between the actual temperature of the body and the outside temperature. The outside temperature is constant, 68. The temperature of the body is changing. What's it called? It's capital T. That's our name for the changing temperature of the body, right? So there you go. That right there is a differential equation because it's an equation that involves derivatives. Happens to only be one derivative, but there could be several. And a solution to this differential equation is gonna be something of the form T equals, like 98.6 minus 5 times T. Like that's the kind of thing that we're after, is what's the formula for temperature? That's what it means to solve the differential equation. So let's solve the differential equation. We're going to do simpler examples of this in a few minutes, but for right now, I'm just going to say we are going to divide both sides by T minus 68. So that guy goes down here. And we're going to multiply both sides by dt. And the k is just sitting over there. Over there on the right, I multiplied both sides by it. So it's kind of strange to treat this as a fraction. We've been treating that as just the symbol that means the derivative, but sometimes it's okay to treat it like a fraction. That's what we're doing here. We did, right. We would do the du dx and then just move the dx over to the other side. That's good. Thank you, Chris. Okay, so we've separated. The capital T is near the dt. There's no little t's, but if there were, we would stick them over there with the little dt. And now what we're going to do is put a symbol in front of both of these. What symbol would make you feel a little bit better about having dt? Where do you see dt's symbols inside of what? Integrals. So what we're going to do is put an integral in front of both sides. We're going to take the integral of both sides. And I like that because now it looks standard, right? It's got an integral and it's got a d whatever. Okay, let's keep going here. So we're going to integrate the left-hand side. Thoughts? Yeah, it is a U-substitution. We would let U equal the whole bottom, T minus 68. What's the derivative of T minus 68? It's just 1 dt. So this is going to become just a du over U. What's the integral of du over U? Is ln. So this is just going to become ln T minus 68. Don't forget the stamp, plus C, equals. Again, you don't need to write this. Integral of k dt. K is a constant. K d. Katie Tunstall, singer. Let's see. Okay, I have made a bad mistake here because the constant you get on the left has nothing to do with the constant you get on the right. So either call it like a plus C and a plus D, or like a plus C1 and a plus C2, just so we really see that they are different numbers. Otherwise, it looked like they just canceled. Okay, so this is good. Next thing we're going to do is abuse those constants C by saying, well, let's just group them together on the right-hand side. And I'm going to define a new constant that's going to be just the difference between the old constant. So just subtract the C1 from both sides and just call it C. So all we did is just combine those constants and called it one magnificent constant over here. Okay, again, what letter were we trying to get by itself? Remember, the goal is something like capital T equals 98.6 minus 5 times little t. So we're going to solve this equation for capital T. So before we do, let's do something else before we solve for capital T. Let's find the K and the C right now. K and C are constants. We got to figure them out based on what's in there, what's up there in blue. So for example, if I plug in 0 for what letter? You got to say lowercase or capital. Little t. Then what do I do with the 90.3? Plug it in for big T. So we go ln of 90.3 minus 68 is equal to K times what's little t? 0 at that moment, plus C. Good. We just found C. So C is equal to ln of whatever that number is, 22.3. Good. What do we still need to find? Still need the K. What haven't we used yet? T of 1. So let's plug in. So ln of what number are we putting for capital T is now 89 minus the 68 is equal to, just going again to that equation, so it's K times T. K times what? 1 is now the little t, plus, and then instead of C, what can we put? ln of 22.3. And right there is enough information to find K, right? All right. So let's do this on the calculator here. Okay, so we do ln of 89 minus 68, that's 21. Guesses? 1 point something, 2 point something, 3 point something, 4 point something.
6, 9.
I'm just looking for what number is before the decimal. Is it a 1? Is it a 2? Is it a 3? Is it a 4?
I'm going to say 0.
Right.
Okay, still solving for K. What do I do to solve for K? Subtract that other guy, right? Subtract ln of 22.3. Okay, so that right there is the value of K, negative 0.06 and change. I'm going to store this as K just so I can refer to it in a little bit. Okay, so we'll come back here and we'll say that K is roughly negative 0.06. And I think that that's just about the end of the game. So now I'm going to copy that green line that's right there at the top of this board. So it says that ln of t minus 68 is equal to, instead of K, we just found minus 0.06 times little t, a copy, and then plus C is plus ln of 22.3. Good. So the only variables left are the true variables, the temperature and the time. That's what we're going to do. Yeah. So let's so before we do that, I'm gonna solve this guy for capital T, but Chris is right. We're going to plug in to find when this poor person was murdered. So let's solve for T. What do we do to both sides? Solving for capital T. I'm going to put an E to both sides. So we go. So it's E to this whole right-hand side, E to the minus 0.06 T plus ln of 22.3, and then add the 68. Yes, after you raise the E. What did we say the temperature of the body was going to approach? Maybe we didn't say it. What will it approach? 68 degrees. If that's the outside temperature, body will eventually essentially reach 68 degrees. Does this confirm that? E to the minus 0.06 T. What kind of a function is that? And what kind of exponential? That's an exponential decay. So eventually what's going to happen to the E to the minus 0.06 T? it's going to head to 0, right? Yeah, it's going to get really close to 0, and then you're going to add 68. The plus doesn't bother me. T is going to be like a million hours, and you'll just get e to the minus infinity, and that's very close to 0, plus 68. So this agrees. It's going to head to 68, and it's going to do so decaying, starting at 98.6, and that's what we're after right now. It's just figure out when this poor guy died. So let's finish. We know that at the moment that this person was killed, if they were healthy, then they were 98.6 degrees. Is that capital or little t? Capital T. So let's go back to this green equation. ln of 98.6 minus the 68 is equal to, just copying the right-hand side, minus 0.06 t plus ln of 22.3. And then we solve for little t. Yeah, so let's come back and just do this on the calculator, and we will solve the mystery. Okay, so ln of, what's in there again is 30.6. I'll just type it just so we see it up here. ln of 98.6 minus 68. Okay, so that's that ln. Still solving for little t. How do we move this? Subtract the ln. Good. Still solving for t. Divide by minus 0.06. We get little t, the time when this person was healthy, was negative 5.27. Chris suggested it was going to be negative. That's negative 5.27 what? Hours from 9 a.m. That was our 0 hour. So yeah, so about 5¼ hours before 9 a.m. is when this person had a healthy body temperature. Okay, so when did they die? Let's see. So at 9 a.m. that brings us back to 4 a.m. but a little bit before that. So say around 3:45. Yep. So the attractive CSIs that we all are would say, oh, a person died between 3:30 and 4 a.m. this morning. Probably they just have an app on the phone that does all this for them, but this is what differential equations is about, is solving problems like this, okay?
On TV, it looks like they just take a look at hours or 10 hours, so they don't actually have to.
I have no idea how they do that. I can't imagine that like there's enough info just looking at a body to tell whether it was 2 hours ago or 4 hours ago. Maybe there is. Maybe with a trained eye you can do that. Yeah. Right. 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 Yeah. So I can buy that, like as a ballpark type thing. But I feel like this is, this is pretty solid. Oh, so you're saying they wouldn't cool off as fast?
Well, I mean, they're not ingredient or anything. I mean, they're cooling off much slower.
Well, it could be if they're insulated, yeah. That's a good question. So I bet there may be variations. We can tweak the formula a little bit to take care of something more complicated, like, yeah, it's got to be an interval. Okay, so let's go back a few pages. Yeah, you got to measure twice. Okay, 51. Oh, wait a minute. Yeah, I think that takes care of it. Yeah, Jeremy's right. I mean, there's a K that's in the formula, and the K, I think, has to do with how fast the person is cooling off. So that you have enough change. Yeah. Sit there. Come on, cool off. Okay, 51. So we're just going to skip around a little bit here. Here are some examples of differential equations. Notice that they are all equations that involve a derivative. Notice that the last equation involves a second derivative and a first derivative. And so let's be clear about the letters. Y is the one on top, which makes it the dependent variable, which makes it the original function. And t is the independent variable, it's the x. And so in plain English, let's take a look at what this equation is telling us. It's saying we're looking for some function y, so that when I take the second derivative of y, and then subtract 5 times the first derivative of y, and then add 6 times the original function, we're going to get 0. Okay, so there's some function out there maybe that satisfies it, but it's not at all clear what it is, right? That is a very complicated idea. 51. Thank you. Yeah, always true. Right. Okay, so that's that. Let's take a look at this part B. We want a function so that when you take the derivative of the function, you get negative the original function divided by 2. Right? Again, I don't know what function does that, but I can start to appreciate how complicated these things are. Part C, if you take the derivative of some function, you get 0.02 times the original function minus 40,000 e to the 0.03 t. T is the other variable, the underneath one. So the t and the y behave very differently. I don't know how to solve that either, but I do know how to solve this one. This says you take the derivative of some function and you get minus t over 2. T is the independent variable. It's like x. You're just looking for somebody whose derivative is t over 2. Well, I know how to find an antiderivative of t over 2, right? Just add 1 to the power, divide by the power. That's the easy one up here. So let's write down our answer for this guy. The function whose derivative is minus t over 2, add 1 to the power, divide by the new power, but there's a 2 down there already. So that's it. That is a function that when you take a derivative, you get minus t divided by 2. But part B, even though it looks quite similar to part A, it's really different. Here, you can't just add 1 to the power up here and divide by the new power. This is not saying find someone whose derivative is t over 2. This is find someone whose derivative is itself over 2. It's a lot different, right? So the roles of these letters, they change quite a bit. So here's how we solve problems like in part B. We're gonna separate these two variables, just like we did on the Newton's law of cooling one. We're going to get the y's over here on the left with the dy, and we're going to get t's, which there aren't any, on the right with the dt. Essentially just divide both sides by y and multiply both sides by dt. Everybody see what we did algebraically? Divide by y, multiply by dt. And now what symbol are we going to put in front of both sides that's going to make us feel a lot better about having a dy floating around as an integral? So we just do the same thing to both sides, integrate both sides. 1 over y dy. And now these are two easy antiderivative problems. Because we've got the y with the dy, we don't have to think about, oh, is it the original function? Is it the independent variable? It's just a letter. It's y and it's dy. It's the same as x and dx. So what's the integral of dy over y? That's ln of y equals minus 1/2 dt. What's the integral? Nope, there's no t in this one. Yeah, negative t over 2. Right? Stamp. C. Technically, there should be a plus c on the left, but we're always just going to group them together in one spot. Any questions on the two separate antiderivatives? Okay, the goal in the body problem was to solve for temperature. Can you guys tell what letter we're supposed to solve for here? There's no t in this one, but it's y. It's whatever the original function is. So solve for the letter on top is the short version of what you're supposed to do. Whatever letter is on top. dy in this case, d capital T. So you look for the derivative and you solve for the letter that's on top. I'm not looking at the right-hand side. T over 2, y over 2, I could care less. It's the derivative. dy, that's the thing that's on top. Okay, so we're supposed to solve for y. So what do we do to get rid of this ln? Raise it to the e. So we go y is equal to e to the minus 1/2 t plus c. It's in the power. That's where it is, right? And then you hit e to that thing, and it's there. It's got the e on it. Okay, let's verify. We just solved a differential equation by separating the variables, y with the dy, t with the dt. In English, this says the derivative of some function is supposed to be the negative of what? That function divided by 2. Okay, let's do that. So here's the verification. So let's start by taking a derivative. So e to the stuff, what do we do? E to the stuff times what's the derivative of that stuff? We go half, right? Plus c vanishes when I take a derivative. That's the derivative. And what I'm supposed to do is compare this to the right-hand side, which says take the negative of the function and divide by 2. Negative y divide by 2. What was the y that we came up with? Is the e to the... the same, right? Do we see it? This derivative is exactly the same as the original function times minus and divide by 2. So it worked. Okay, so we're going to spend a bunch of time today solving differential equations that look like this. It's a special kind of differential equation that is separable because we were able to do some algebra at the start and get the y over here on the left with the dy and get the t over there on the right with the dt. We cannot do that in part C because of the subtraction there in the middle. How could I get the y's on the left? Maybe subtract the 0.02y, but then I don't know what I'm going to end up with. I mean, it's this and then subtract 0.02y, and I can't imagine having a negative, like the 0.02y needs to be attached to, right, multiplied by the dy. I can't make that happen in this case. Okay, so then that's a good idea. So we can add the 40,000. So we got dy dt plus the 40,000. We don't need to copy this 0.03t, and then divide by the y, right? And that's equal to, I guess, 1 is what's over there on the other side, or 0.02y. Still have a problem here because even as I take an integral, I still have a plus sign in my integral. That's no good. I've got this dy dt plus. Yeah, so you can divide everything by dy, and that's going to end up with a dy under this guy, and it's a problem. So when I say solve, when I say separate and get the y's with the dy and the t's with the dt, all you're allowed to do is multiply and divide. As soon as you add or subtract, you're done. We can't do any addition or subtraction. So part C is a differential equation that we just can't solve at this point, and we're not going to this semester. Want to learn how to solve it? Take a course called Differential Equations. So there's a technique, but it's not as simple as this separating. So I just want to be clear that separating is a special kind of differential equation. That's not how we solve all of them. Let's take a look at part, yeah, Topher? Yeah? Yeah, it's the cliffhanger. That's how we keep you coming back. Okay, part D, again, says find a function so that when you take the second derivative of the function, minus 5 times the derivative of the function plus 6 times the original function is supposed to all magically cancel and get 0. So it's really hard to solve that differential equation. We're not going to have the tools to solve it this semester. But if I just give you some miracle, and I say, hey, I think the solution is 5e to the 2t. It's easy to check whether or not I'm right. And this is something I'd like you to be able to do on the final exam. How are we going to check to see if this is a solution? So is this a solution? We're going to take two derivatives, and we're going to plug everything back into that equation. And if it works, if the equation is true, then yes, I've had some miracle and I found a solution. And if it's false, then what I've provided is not a solution. So let's take two derivatives. Y prime. Yeah, it's going to become 10e to the 2t, right? Because the 5 stays, e to the stuff you copy, and then times what at the end? Times the derivative of the stuff, so times 2. Second derivative, 20 e to the 2t, right? Times another 2. So now we got to see if it actually works. You're going to take those three things, you're going to plug them into that equation, see if you get 0. Go ahead, take a moment, plug everything into the equation, see if we get 0. So does it work? Is it equal to 0? It is equal to 0. So yes, we have a solution. 5e to the 2t, wherever it came from, is a solution. Okay? So it's hard to solve differential equations, but it's easy to verify that something is a solution. Any questions on that? So in terms of where I came up with 5e to the 2t, I took a course called Differential Equations. I'm sure I got an A. I solved it from that equation. In fact, I solved it in front of you from that equation. So there's not a lot of work to do, honestly. I'll say that there is, so first of all, I'll say you can put any number you want there in the front and it will work. So 7e to the 2t will also work. You can check that later. If you want a challenge, there is a different number I can put up. 2 is special. You can't just put any number up here and hope it will work. But there is one other number that you can put up there instead of the 2 that will make it work. So try -2 and see if it works. Try a different number, or maybe there's some process you can try to figure out what the other fundamental number is that goes up there. There's only 2 of them. I gave you one, just for fun. Maybe. Okay, I think that is good. Let's have you guys skip to this page right here, 53. Page 53. 0 doesn't work, does it? 0 doesn't work, does it? 0 next to the t. You can check. I don't think it works. Okay, page 53. You are going to try to solve as many of these separable differential equations as possible. Remember, the first step is to get the, we have x's instead of t's, so you get the y's with the dy, the x's with the dx. And one hint when you get down to part C is that y prime is also known as dy dx. So that might be a good thing to do, is replace the y prime with dy dx, right? So let's see how far we can get. We've got about 27 minutes. I'll walk around, raise a flag if I can help, and work with each other.